All right, welcome back, everyone. Today we're going to just jump in and continue in on our 12 parent functions. We covered 5 of them already. That was x, x squared, x cubed. We did root x, and we did 1 over x. So we're going to continue on today with the next 4 parent functions. So let's change this color to be a little less violent and see what we get. So same things we talked about last time: domain, range, extrema, asymptotes, even odd symmetry, continuity, and boundedness. So next one we're going to do is the exponential function. Now you really could choose any exponential function to use as your parent. We're going to use e to the x because it's really important in some of the stuff we're going to be doing in pre-calc and also in calculus. So e to the x, you may have seen before. E is a number. E is the number 2.718281824599045. And this is one that's actually an easy number to remember. 2.7, you got to remember. 1828 happens twice. That was the year Andrew Jackson was president. Then we have 45, 90, 45, right triangle. Kind of cool. I don't know what comes after that, but cool little party trick if you want to say, hey, guess I know a few digits of E, I guess. Sure. Parties I go to anyway, super nerdy. So f of x equals e to the x. E is just a number. Exponential functions all have the same shape. They look like this. E to the x grows very, very, very quickly. And in fact, it grows faster than any polynomial you can think of. And it has some really cool properties that we use in calculus. So e to the x, great function. Domain, all real numbers. Range, open parentheses, 0 to infinity. We can't get 0. Right? Remember, if you do a negative number, like if you do e to the negative 10,000, so a really negative number, that is 1 over e to the 10,000. That's going to be a really big number on the bottom of a fraction. It'll get very small, but it won't ever hit 0, right? The more and more negative I go, that puts us bigger numbers to the bottom of a fraction, but it'll never get to 0. More positive you go, obviously, positive number to a positive power are going to be getting very big. It's continuous everywhere, increasing everywhere, never decreasing. Symmetry has none, right? Because if you had even symmetry, there'd have to be something up here. And if it had odd symmetry, there'd have to be something on the bottom, which we don't have. We are bounded below. Extrema, none. Because it looks like we approach 0, but we never get there. And the further left we go, the closer we'll get. Asymptotes. We have a horizontal asymptote at y equals 0. End behavior. As x approaches positive infinity, the function definitely goes up to positive infinity. And as x approaches negative infinity, the function values are getting closer and closer to 0. Nice. Okay, next function we're going to do is the inverse of e to the x, actually. It's called the logarithmic function, natural log. This is f of x equals ln x. ln, I think, is French. I think it's kind of like in Spanish and French. In the Romantic languages, they do the adjective first. Sorry, the adjective last. So logarithmique naturel or something like that. I butchered the French, I'm sure, but it's log natural instead of natural log. So this function, like I said, it's the inverse of e to the x, and you may remember that if you want the inverse of a function, you reflect it over this line. Anything that's horizontal becomes vertical. So instead of having a horizontal asymptote, it turns out to have a vertical asymptote. It looks something like this. It gets very, very flat. The other one grows really fast. This guy gets very, very flat. Domain, I can only plug in positive numbers. No 0, because remember, it never reaches 0 on e to the x, doesn't here either. Range, though, is all real numbers. Notice the domain and range flip-flopped. That happens with inverse functions. Very cool. Continuous on its domain. No discontinuous points there after it starts off at 0. It's increasing on all real numbers. Sorry, on its domain, I should say. Never decreasing. Symmetry. We don't have even symmetry because there's nothing on this side, and we don't have odd symmetry because it won't rotate and give us anything. So no symmetry. We are not bounded. This is interesting. It looks like it gets really flat and approaches a horizontal asymptote. It actually never does. No extrema. Asymptotes, we have a vertical asymptote at x equals 0. Notice once again that switched. Y equals 0 is our asymptote here. X equals 0 is now. End behavior. As x approaches infinity, the function is going up forever. Even though it looks like it's flattening out, it always goes up. And as x approaches, we can do that 0 from the right thing again. because that would really be the end behavior on the left, because it doesn't go any further. The function values freak out and go to negative infinity. Cool. All right, natural log. So next one we're going to do is sine of x. So sine and cosine we're going to learn a lot more later on when we're doing trig, but this is sine. I should have written that the other way. So sine is the function, and f of x equals sine x. So remember, this is the circular function. Starts with 0 right here. Sine of 0, it's the vertical coordinate, is nothing. It rises up to 1, and then it drops back down to 0, and then it goes down to -1, and then it comes back up to 0. And this goes forever because your radians can go as long as you want in each direction. And the arrows here mean the pattern continues, doesn't mean it goes down forever or up forever. Domain is all real numbers. Range is -1 to 1 inclusive because that's the top and bottom of the unit circle. We are continuous everywhere. We increase, this is interesting. So this is -pi/2. This is +pi/2. So we increase from -pi/2 to pi/2, and then that happens every 2 pi. So -pi/2 to pi/2. Then this would be at 3 pi/2, and then it would stop increasing again. This is 2 pi. So we got to go beyond 2 pi. This would be what, 5 pi/2? 3, 4, 5. Yep, 5 pi/2. So what happens is every odd pi/2, we start increasing again. So what I'm going to write here is it's periodic. We're not going to deal with too much of the like plus pi n stuff right now. We'll do that later on. So periodic. Because every period it increases, right? Same thing with decreasing. It decreases periodically. Symmetry. This is an interesting one. It doesn't have y-axis symmetry because then I would need a bump over here to match up with this one. But if you spun it around this point, obviously it goes on forever in both directions, but if you spun it around this point, this hump would go here. This hump would go here. It does have odd symmetry. This is a trick we haven't learned, but sine of -x is always equal to sine x. You can see that from the circle. If you go down just a little bit, sorry, negative sine x. If you go down just a little bit in the unit circle, and you go up just a little bit, that distance is the same as long as it's the same angle, but it's opposite each other. So that is -f of x, which tells us that it's odd. We are bounded. We are bounded in general because it's bounded both below and above, right? So we can just say it's bounded. Extrema, once again, we have periodically. No asymptotes. And end behavior, really as x goes to positive infinity, it's just waving around, so it doesn't approach a horizontal asymptote, and it certainly doesn't have any vertical asymptotes. So none that's very exciting. Cool. Last one for this video is cosine. F of x equals cos x. Once again, this is a unit circle thing. We start off at +1, we decrease to 0, then we go down to -1, then we go to 0, then we go back to +1. So cosine starts when x is 0, it starts at 1, and then it decreases down to 0 and all the way down to -1. Something like that. Nice. Domain, all real numbers. Range, -1 to 1 again. A lot of this is the same as sine. Continuous on its domain. It increases periodically. It decreases the same periodically. Ditto mark means the same thing as above. Symmetry. We actually this time have even symmetry because if you folded it over the y-axis, you would end up with the same graph. So this is even. And we are bounded in general because we're bounded both below and above. Both below and above. We have a line we could draw. It would never cross. Extrema is periodic as well. Let's see. Asymptotes, we don't have any. And our end behavior, once again, if we go to the right and the left, we oscillate. It goes up and down. But I'm just going to say never. Or none. None would be better. Cool. Alright, I think that's it for this video. So hopefully you learned a little bit more about the parent functions. I will see you in the next video to do the last 3, and they're a little bit different, so make sure you check that one out. Love you guys, that's why I'm here. Have a great day.